his PhD in theoretical physics at the University of Cambridge in 1997. His scientific deliverables include 234 peer-reviewed publications, 3 single-authored books, hundreds of proceedings papers, technical reports, mission studies, oral communications, and talks at scientific meetings. He has been the PI of 11 founded groups grants, as well as a member of several formal collaborations, for instance, Espresso, Euclid, Andes, LISA, and SKA. On the human resources side, he supervised dozens of PhD and master's theses. Particularly, I would like to mention also that he supervised in the order of hundreds of undergraduate and high school projects. He has a prolific research on fundamental cosmology and particle astrophysics, as well as he's very active with outreach activities, as this one we are going to have through this week. So in order to take advantage of having him here, let's hear him. Professor, thank you again for accepting the invitation, and feel free to start. Thank you.
Thank you very much. Hello, everyone. My name is Carlos. You also see my email on the bottom of the slide, so feel free to use it, contact me later on. So first of all, apologies for not being there in person. These months are quite busy for me, so I'll do the best I can remotely, and we have a Discord channel that I'll come back to in a moment to make things a little bit easier. So you already know a little bit of my background, so I won't repeat it. You can see some photos of my scientific career, one way or the other. So the first one on the top left is my high school. So I was born in Viana do Castelo in the north of Portugal on the Atlantic coast. So yeah, I started my university training at the University of Porto. Then I moved to Cambridge, where I stayed for quite a number of years. I came back to Portugal more or less full time in 2007, and then gradually I got involved in various different things. My initial training is as a theorist, and I think this will be clear from these lectures. But gradually I got involved in several ESA and ESO projects. So I'm heavily involved in the ELT in several different ways, including the construction of the Andes spectrograph. Some people in the room are also involved in, and I'll mention this later in the week. I'm also involved in Euclid, as was mentioned. And just as a small advertisement, in just about 24 hours, Euclid will publicly release its first 5 images. So tomorrow afternoon, European time, tomorrow morning, your time. Make sure you have a look at them. They're really beautiful images and well worth watching. And I'm also heavily involved in various education and outreach activities, and I won't cover them in the lectures, of course, but I'm happy to discuss them with you offline if anyone. Since I use the name Find the Sky for these lectures, I also want to spend a couple of minutes explaining what this is. So it's simply the name of my current main research grant. So it's funded by FCP, the Portuguese Research Council. And it involves people in Center of Astrophysics at the University of Porto, but also small groups of collaborators in Cambridge, in Paris, and in the Terrestrial Observatory in Italy. Just to give an idea, there's more than 30 people involved, from senior researchers to postdocs, PhD students, and also a good number of younger students, so master students and even undergraduate students. And indeed, we also try to involve even high school students, give them a little bit of a first glimpse of what it is to do research in physics and astronomy and so on. And again, happy to talk about this some other time. And the Find the Sky project has 6 scientific goals. So as some of you know already, and others will certainly find out in the future, whenever you apply for funding, whenever you apply for a research grant, you need to specify, among many other things, what are the scientific goals, the questions you want to address. And this project has basically 6 of them. And in these lectures, I will talk about 4 of them, starting with understanding whether or not the laws of physics we know in the lab are universal, i.e., whether they apply as well to the rest of the universe in other places and at early times, understanding behavior of gravity, understanding whether it's really just geometry, as Einstein suggested, or whether it's something different, understanding the physics of the recent acceleration of the universe. So why is the universe accelerating right now? What is the physical mechanism that is responsible for that? And also, because answering these questions requires new and improved facilities, how can we build new and improved facilities to try and address these questions? So this includes things like the Andes spectrograph, which again, people in the room are also involved in. So I will mention these questions during the week. There's 2 other scientific goals of the project that I don't have time to talk about. So one has to do with fossil relics of the physics of your universe, things generically called topological defects, and also with various education and outreach activities we have for mainly high school students. Again, we can discuss them somewhere else. Okay, so before getting into the material, let me give you some sort of preliminary note and a little bit of the philosophy that I had in mind when putting together the material for these lectures. So the first thing is that this is a very broad and interdisciplinary topic. So we'll cover things from fundamental theoretical physics to observational astronomy, even to laboratory experiments. So it's a very broad subject, and I cannot cover everything in detail. But what I will do is to give you an overall view. So try to make sure that by the end of the week, you more or less understand what are the open questions in this field, why people are working on it, why people like me are really excited about it. So try to give you a sort of bird's eye view of the field. But in order to cover all this material, I will have to skip the technical details. And one of the things that we'll notice as we go through the material is that you'll see quite a lot of plots, not in the most introductory part, but after a while you'll start seeing a lot of plots. There will also be a reasonable number of references that you can look up and read later, but you'll see very few equations in my slides. And this is more or less deliberate. It's by design. So I know not many of you are cosmologists. So you're working on other equally interesting and exciting fields. Some of you are younger students, you're doing masters or things like that. So my philosophy for a course like this is you don't really need to know the technical mathematical details. You can always learn them later on if and when you want to dig into these issues a little bit more detail. So my goal here is to give you an overall view, and then you can take it in any direction you want. I'm always happy to give you more technical details later on if you want, so you can ask for them, but I want to make sure I cover a good number of things in the time that I have. So one thing that I will not cover in detail is standard cosmology. So some of you will have taken already introductory cosmology courses, others probably not. That's not really an issue, and so I hope it will not be a limitation. If you do want to have a relatively short but useful introduction to standard cosmology, one place that I can recommend are the lectures that Martin Kunz gave 4 years ago in the same series. You can have them, you can see them on YouTube, and you can learn from them. Okay, so the other limitation that we have to deal with is that I'm not there to discuss things with you over coffee breaks or lunch or dinner. And this is where Discord gets useful. So for the sake of efficiency, I would suggest that if you have verbal questions, mainly ask them at the end of each lecture. But if you have questions while I'm talking, do write them down on Discord. So I will not check Discord while I'm talking, but writing them down is just a way for you not to forget them, and also for me not to forget that I'm supposed to reply to them at some point. So I'll try to not spend more than, let's say, 55 minutes in each of the lectures, and the rest of the time we have for questions. And I can look at Discord at that time and answer questions that are there, or I can answer questions that you can ask verbally. But I can also ask questions on Discord offline, any other time. If you're later on looking at the notes that you take through the lectures and find something confusing or unclear, just feel free to ask that question on Discord, and eventually I will answer it. And this applies this week, but also in the coming weeks. I'm very happy to keep interacting with you later on, and even to organize some Zoom calls to answer doubts that you might have in more detail. So please feel free to ask questions there, and I'll do the best I can to answer them. I don't know how many students are registered in the course. I'm not sure if everyone's on Discord yet, but if you're not, we can add you later, and you can join the discussion. Okay, and with that said, we can move to the actual content. So today we'll mainly have a conceptual introduction and discuss some relevant theoretical concepts that we will use for the rest of the week. We'll see when we stop. So as I said, my plan is to stop for about 55 minutes and then stop, but we'll see how much we talk. Okay, and let me start with a sort of allegorical exercise or an analogy. So suppose you're given a picture like that and asked to determine whether or not this is a dog. Maybe a dog, it may be a cat, maybe something else. There are several different ways you could go about answering the question. You could just try and get a better picture, maybe clean the image, maybe get a slightly better image, and eventually you might find out it's actually a cat. Now, the point to keep in mind throughout this week, the context of my lectures, is that there are several different ways for you to find out whether this is a dog or a cat. And in particular, you don't even need to have a picture of the entire animal. You don't need to look at the entire animal. If you know about DNA, a few cells will be enough. So that is the analogy to keep in mind. So what am I talking about specifically? Well, we've known for the last 20 years or so, which is a long time for you, a slightly less long time for me, that the universe is accelerating. And the observational evidence for the acceleration of the universe tells us that there is something about our theories of cosmology and fundamental physics which is at least incomplete and possibly might even be incorrect. Why is that the case? Well, the question is whether or not this component that is accelerating the universe, what we call dark energy, because we don't have a better name for it, whether or not this is a cosmological constant. And whether the answer is yes or no, the implications are dramatic. If dark energy is indeed a cosmological constant, so what's called in the context of quantum field theory, vacuum energy, if it is a cosmological constant, well, that's fine in principle. Maybe that's how nature works. But the point is that the observed value, the measured value for this cosmological constant, which astronomers can measure, is about 120 orders of magnitude smaller than our current quantum field theory expectations. So quantum field theorists can calculate in their theories this vacuum energy density, and they find out values that are many orders of magnitude larger than what astronomers measure. Depending on how you count this, you can say it's 120 orders of magnitude, or you can say 60, or you can say 30. In any case, this calculation is clearly wrong. Right? It's off the real value by many orders of magnitude. So there's something wrong in that calculation, and presumably there's something wrong in our views of quantum physics. On the other hand, this dark energy might not be a cosmological constant. Then, as a particle physicist, you just need to provide a mechanism to force the real vacuum energy density to be zero. And in principle, you can do that. You can invent or postulate some symmetry or some conservation law that will do this for you. You might think this is cheating a little bit, but in principle, it's a legitimate answer, because if you postulate that symmetry, then that symmetry will have other consequences elsewhere. But you also need to provide some additional mechanism that gives you the acceleration of the universe, which does not rely on the cosmological constant. Such mechanisms exist. The simplest way to go about them is to invoke what's called a scalar field. We know that scalar fields exist in nature. There's at least one scalar field, which is the Higgs field. So there may be others with cosmological roles. But one consequence of having a dynamical scalar field giving dark energy is that the Einstein equivalence principle will unavoidably be violated. In that case, general relativity is not correct, gravity is not purely geometry, and so on. So ultimately, and this is the message you should take from this slide, the fact that we see the universe accelerating today tells us that there is something in our view of the universe, whether on the particle physics side or on the gravitational side, that we haven't quite understood, and obviously want to understand it a little bit better. So there is new physics out there waiting for someone to discover, whether it's my generation or your generation that does it, we'll see. But in any case, we must search for, identify, and ultimately characterize this new physics, understand where it comes from, and so on. And for this, we need new and better tools, new astrophysical facilities. So the purpose of these lectures is to highlight one possible way of going about this task of understanding this physics, which essentially involves high-resolution spectroscopy. So astrophysical high-resolution spectroscopic observations. So I will give you the status of the field now, and I'll also outline towards the end of the lectures where the field is going, or at least where I think the field is going, and what will be necessary for this to be not only an active field of research in the 2030s, which I think it certainly will be, but what is necessary to make this a competitive field in comparison with all the other developments in astrophysics and cosmology that happen. Okay, so that's our goal, and in a sense, it's the question to keep it in the back of your mind. And just as a small historical note, I also have some interesting history of ideas in astronomy and physics. So just as a small historical note, we have this dark universe these days. I think you all know that 95% or so of the content of the universe is stuff that we've never seen in the lab. So it's dark matter and dark energy. Again, these are just names because we don't have any better description for them. So the only evidence we have for them is indirect evidence coming from astrophysical and cosmological observations. But there's maybe some interesting analogies with the history of astronomy in the 19th century. So you probably heard of the history of the discovery of the planet Neptune. So when people discovered Uranus and started calculating its orbit according to Newtonian physics, they soon discovered that there was a difference between the calculated orbit as predicted by Newtonian physics and the orbit of the real planet Uranus on the sky. And in principle, you could explain that discrepancy in two different ways. You could say maybe Newtonian physics does not apply on these large scales, or you could say, I believe Newtonian physics is correct, and I'm going to use Newtonian physics to predict where in the sky I should have some other planet whose gravitational pull will explain the difference between what I calculate and what I measure. And people actually predicted, discovered mathematically Neptune before it was discovered on the sky. This is mainly the work of Urbain Le Verrier in France and to a lesser extent John Couch Adams in the UK. So we had a dark planet, Neptune, that was eventually discovered, and it was a real planet. But this coin has another side, which is non-discovery of the planet Vulcan. So just like there was a discrepancy in the calculated and observed orbits of Uranus, there are also discrepancies between the calculated and observed orbits of Mercury. And because of Mercury, people more or less tried to apply the same recipe and postulated or predicted, assuming Newtonian physics to be correct, a new planet, which they baptized with the name Vulcan. And there's lots of efforts in the second half of 19th century to try and discover Vulcan, but it was never discovered because in this case, the answer to the problem was that Newtonian physics is not accurate enough to predict the orbit of Mercury. So there was another dark planet here, Vulcan, which is actually not a real planet. So the important point here is that we have two seemingly identical problems, a difference between a calculated and an observed orbit of a planet. In one case, the standard model, which at that time was Newtonian physics, was correct, and it allowed the discovery of Neptune. In the other case, the standard model was not correct, and the solution was to change or to upgrade Newtonian physics. So the interesting analogy is here that we don't really know in what side of this divide dark matter and dark energy will fall. Most people believe that dark matter is a particle, so a real substance that eventually we'll discover in the lab. This may or may not be correct. And similarly for dark energy, it may be a vacuum energy density indeed, so a sort of fluid with some very peculiar properties. But it could also be an apparent manifestation of a different behavior of gravity on large scales. I think it's interesting historically to keep various possibilities in mind and see how people address the problem. Now, I mentioned the acceleration of the universe as a hint of new physics, but even in particle physics, you can think of the existence of various clues that tell you that our view of the universe is not fully complete yet. Because there's at least three facts that are well established experimentally, which at least in the plain vanilla standard model particle physics cannot explain. So one is the presence of neutrino masses. So this is a sort of add-on to the standard framework. They don't exist in the simplest version of the standard model. A second one is dark matter, which I already mentioned briefly. So there's no standard model object, so whether it's an astrophysical macroscopic object or a point particle, that can account for all the dark matter that seems to be required by observation. So it's clearly something beyond the standard model. And the third piece of evidence, which might be a bit more obscure to most of you, is the size of the baryon asymmetry of the universe. And here I have to mention the word size, because in the standard model of particle physics, there is a mechanism to generate a baryon asymmetry. But given what we know experimentally about particle physics, so given what we know about the model parameters, this mechanism is not strong enough, is not sufficient to give you the baryon asymmetry that is observed. So again, you need some extension to the standard model to make everything come out right. And to some extent, in the case of particle physics, where there is a standard model that has a longer history than the analogous standard model in cosmology, it's precisely our confidence in the standard model, which has been extensively tested in particle accelerators, that leads us to the expectation that there must be something else beyond it. So that's one one point to be made. The other point is that if you look at the list of three things, all of them have obvious implications for cosmology. This is another point that I want to emphasize here, and that I think we will come across in the rest of these lectures. There's unavoidable links between fundamental particle physics and cosmology. And indeed, these days, a lot of the progress in particle physics is becoming dependent on observational cosmology. So the two fields are inextricably linked. So it might work on one side or on the other side, but whatever you do on one side has implications for the other side, and people on the other side will be interested in your results. So in a sense, this makes the field a little bit different, and also perhaps a little bit hard to get into because it's very interdisciplinary. You need to know a lot of material, but it also makes it really exciting to work with. Right? Okay, so as I said, the approach that we're going to take relies on high resolution spectroscopy. And a second historical note for you to keep in mind is that high resolution spectroscopy has played a key role in fundamental physics developments. It was essential to the development of quantum mechanics. So the observations of the discrete nature of spectral lines were part of the motivation for people to start scratching their heads and eventually come up with the description of the quantum universe. Another example would be the photoelectric effect, which was, of course, experimentally seen before it was fully understood. Some decades later, precision spectroscopy was crucial to the confirmation of quantum electrodynamics. So one example you can read about later if you want is to do with the lamp shift. So it was calculated and then confirmed experimentally. And in the last 15, 20 years, there are several Nobel Prizes in physics, which are one way or the other related to state-of-the-art high-resolution spectroscopy. So this is just to emphasize that high-resolution spectroscopy has played already a key role in the development of our view of the universe in the context of fundamental physics. But in modern astrophysics, making use of ongoing improvements in precision and accuracy and stability of high-resolution spectrographs, which are now fiber-fed shell spectrographs, and they're not the old split spectrographs, gives high-resolution spectroscopy an opportunity to again impact fundamental physics, either by testing some of the key assumptions of the standard cosmological model and of the standard model of particle physics also, but also in identifying this new physics as I mentioned already. So what's our DNA in this context? Our DNA will be more or less like the spectrum that you see on the slide now. So this is a high-resolution spectrograph. It's a cartoon. So it's a high-resolution spectrum. It's a cartoon. For most of what I'm discussing in observational terms, we're going to look at low-density absorption clouds along the line of sight of a bright quasar. So the quasar, for us, is just providing backlight. So we'll have an emission spectrum. Bluewards of the spectrum will have the Lyman alpha forest. Redwards will have some absorption lines. And these come from a low-density absorption cloud, as I said, that happens to be along the line of sight of the quasar. And essentially what they're going to do is to characterize the physics of physical processes happening in these low-density absorption clouds. We're going to be able to measure the define structure constant in this cloud. So essentially test whether the strength of the electromagnetic interaction at that time and in that place in the universe, so in that absorption cloud, was the same as we know it in the lab. We're going to be able to measure other dimensionless constants like the proton to electron mass ratio using molecular vibrational and rotational transitions of molecular hydrogen and possibly other species. And we're going to look at the position of the absorption features of Lyman-Walter forest to see or to try and measure directly the expansion rate of the universe, so to see the universe expanding in real time. So this is what's called redshift drift. So I'll talk about all these things in more detail later in the lecture. So at the moment, I'm just giving you an overall view of where we're going. But one thing to keep in mind in this picture is that we're not measuring these things at the quasar itself. So the quasar can have lots of messy astrophysics. It may be a variable source, etc. We're not measuring anything at the quasar itself. The quasar is just a bright light, it's just backlight to illuminate the absorption clouds we're studying. So don't be confused. So don't think that we're measuring things at the quasar. We're measuring things in low density absorption clouds along the line of sight of a bright quasar. In principle, the physics of those absorption clouds is a little bit simpler, and if we know it well enough, then we can use it as a fundamental physics probe. But I will come back to this image later on. I've also been using the word fundamental physics a few times already, so let me spend a couple of minutes defining what I mean by fundamental physics in this context. So basically, I mean one of two things. So first, testing the fundamental laws and symmetries of the universe. So testing the Einstein equivalence principle, for example. I'll come back to that one in a moment. Testing the behavior of gravity on various scales, so on small scales, large scales. Understanding the overall structure of space-time, how many space-time dimensions there are, for example. As you probably know, in most extensions of a standard model, there are additional space-time dimensions, something that in principle one can test. Testing the foundations of quantum mechanics and so on. So understanding the broadest picture of how the universe works. And then a second component is characterizing the building blocks, so the main ingredients of the universe. This includes things like scalar fields. Again, the Higgs is one example, and as you'll see, scalar fields are commonly involved and invoked in theoretical cosmology these days, just because they're nice and simple things to work with. But understanding the particles that make dark matter, if indeed dark matter is made of elementary particles. Other things like magnetic monopoles that we thought, or still think, were formed at some point in the early universe, but we don't see them today. In the context of string theory, there's fundamental objects are what's called fundamental strings, and one should understand what they're like and so on. So understanding the building blocks of the universe, as I say. And the point here is that in most fundamental theories, so which are extensions of our current standard model, which is essentially a low energy standard model, and therefore presumably a low energy limit of a more fundamental theory, there are physical mechanisms that violate up to some level a lot of these standard principles. So as we'll discuss in more detail tomorrow, fundamental couplings are not really constant. They are dynamical, so they can evolve in space and in time. And this will violate the Einstein equivalence principle. The behavior of gravity can change on large scales, and this will impact how the universe expands. Sometimes the space-time structure So the microscopic structure of space-time is modified, and in some cases, this can violate Lorentz invariance, for example. This doesn't happen in all theories, but it certainly happens in some of them. So when you try and go beyond the standard model and make new predictions, sometimes you come across processes that violate assumptions of the standard model, and these assumptions are tested, at least to some level of precision and accuracy, and sometimes you're limited and constrained by those experimental and observational facts. So you don't have infinite freedom in expanding these models because there are very tight constraints on some of this. Okay, so one of the things we've learned from the LHC, among many others, is the fact that there are scalar fields as part of the building blocks of nature. So this is something that we only learned in 2012, because none of the other ingredients of the standard model involve scalar fields. They involve other kinds of degrees of freedom. So now we know that the Higgs field is among the building blocks of nature. So scalar fields are part of the building blocks of nature. The Higgs field cannot really have a cosmological role, but if there is one scalar field in nature, then surely nothing prevents other scalar fields from existing in nature. And the important point, and in a sense, this is the perhaps the most important idea of these lectures, whenever you have a scalar field in your theory, so something that is dynamic or that evolves as the universe expands rather than just a constant, like a logical constant. So whenever you put a scalar field in your theory, so in your Lagrangian, and the natural expectation is that this field will couple to all the other degrees of freedom in the model. Unless you postulate some symmetry, some new law of nature to suppress these couplings. And the technical argument for that is at the bottom of the slide. So I wrote it there so you can see it, and we don't need to discuss it now because it is a technical point. So don't worry too much if you cannot follow it. So the point to have in mind is that if you put a scalar field in your theory, the natural expectation is that it will couple to everything else. And if these couplings are there, then you should expect long-range forces, so kind of fifth force in nature, and the variation of these couplings, so what we commonly call very fundamental constants. And the simplest example of that, and the more interesting one observationally, just because it's comparatively easy to test, is that if you couple this scalar field to the electromagnetic sector, then you expect space-time variations of the fine structure constant. And this, as I said, is something that you can measure, you can test in the lab and in various astrophysical settings. And we'll discuss several of these tomorrow. So testing whether or not these couplings are really constant is useful in and of itself. And even if you get no results, if you get results consistent with no variations, that will constrain theoretical models, because all of these theoretical models predict that there should be variations. So if you provide constraints on these variations, you're automatically constraining these models. You're telling theorists that they don't have infinite freedom in their models. They must satisfy these constraints. And in fact, these null results can even be competitive with cosmological observations. So these astrophysical measurements, spectroscopic measurements, can be competitive for a lot of cosmological models with constraints that you get from cosmic microwave background, supernovae, very acoustic oscillations, and so on. Again, we'll see examples of this. So even if you find no detection, if you find no variation, just improving limits is useful. So the question, as I said, is does the Higgs field has a cosmological counterpart? Um, we don't know that. We don't know the answer. Um, but for any of you working in cosmology, you know this already. Um, it's hard to find a cosmologist these days, or at least a theoretical cosmologist, who hasn't used a scalar field in his or her work, because they're basically everywhere. Um, and you might ask, if you're not a cosmologist, well, why are cosmologists so crazy about scalar fields? Well, there's two or three answers to that. So one is we are a bit lazy, and scalar fields are just simple and easy to work with. Um, but they're also popular because although when you put them in your theory, they do have some effect, like these variant couplings, um, they leave other things relatively unchanged. So, for example, you can put them in your theory and still preserve Lorentz invariance, which would not be the case if you had a theory with a vector field or some additional fermions and so on, cosmological rules. And of course, if you break Lorentz invariance and things like that, then you immediately run into trouble with special relativity. So in this sense, scalar fields are a bit more harmless, right? They allow you potentially useful cosmological effects without messing up the rest of your theory. And there are several examples of contexts in cosmology where scalar fields are common these days. So we use them to explain a period of exponential expansion in the early universe, or what's called cosmic inflation. Um, they're used to describe cosmological phase transitions and their results, something called cosmic defects or topological defects, which form unavoidably at these phase transitions. They're an explanation for this dynamical energy that is accelerating the universe for recent times. And you can use them to describe the varying fundamental couplings that I also talked about. So in these lectures, we'll talk about the last two of these of this context. We'll discuss the other two. But one point I want to emphasize here is that whenever you put a scalar field in your theory, you don't get just one of these consequences. Typically, you get several of them at the same time. So one example, and this is how the last two are connected, if you have a dynamical scalar field giving you the dark energy, then that scalar field will unavoidably also give you a varying fine structure constant. So you can use measurements of alpha, the fine structure constant, constraints on alpha, to constrain dark energy. So this is important because it provides you a consistency test, right? Because you can say, if I have a scalar field that gives me dark energy with some properties, then I predict there should be a variation of alpha at some level. And then you can take that prediction and go out, look through your telescope or through your data and see whether that prediction is confirmed or not. So these consistency tests are important, also because of an issue of redundancy, right? If one day we confirm one of these things, we're going to need redundancy. We're going to need evidence for this new physics in multiple different contexts. And this is where these consistency tests play a role. So to take one example, you students are probably a little bit too young to remember this, but your teachers and older colleagues will remember when the observational evidence for the acceleration of the universe started appearing from type 1a supernovas. Initially, people were very skeptical. They were saying, "Oh, I'm not really sure if supernovas are standard candles. Maybe there's some systematics. Maybe the analysis is wrong somehow." But eventually, the very same evidence also started appearing from cosmic microwave background, variant acoustic oscillations, various large-scale structure observables, and so on. And now, even if for some reason you don't believe supernovas, there is evidence at many standard deviations that the universe is really accelerating. So this is what I call redundancy. Whenever someone claims new physics, you must have evidence for it in several different independent ways, different kinds of data, different kinds of systematics, and so on. And this is where these consistency tests are important. And again, later in the lectures, I will give you some examples. Okay, let me also say a few words about the equivalence principle. You may have discussed this if you had a relativity or course, but if not, I want you to at least have an idea of it. In principle, when we use the word mass, we can mean two or at least or even three different things. We can talk about the inertial mass, which just quantifies the proportionality between a force applied on an object and how it accelerates. So this force need not be a gravitational force. You push some object, it reacts, it accelerates in some way. The mass, the inertial mass tells you how hard or how easy it is to accelerate that object. So that's inertial mass. Then you have gravitational mass, which measures the ability of an object to attract or be attracted gravitationally by another body. And in principle, here you could have a subdivision. You could talk about the active mass, which is how much a body attracts another one, or the passive mass, which is how much a body is attracted by another one. And in principle, these two could be different, but in Newtonian physics, they are not. That's essentially the content of Newton's third law. So in Newtonian physics, active mass and passive mass are the same. You can just call them gravitational mass. But you could think of alternative gravitational theories where the two would actually be different. And Newton's equivalence principle essentially says that the inertial mass is always proportional to the gravitational mass. And from this, we get the universality of free fall. So every object falls the same way in any gravitational field. But strictly speaking, in Newtonian physics, all you can derive is a proportionality factor between the two. What Einstein did, and this is one way of phrasing a part of the Einstein equivalence principle, is that in general relativity, you don't have a choice about this proportionality factor. General relativity, the proportionality factor is exactly 1. So inertial mass is the same as gravitational mass. Pragmatically, it's convenient to separate the Einstein equivalence principle into 3 components, essentially because there are 3 things you can test in different ways. The first is what's called the weak equivalence principle. So the trajectory of a freely falling test body is independent of its mass, internal structure, composition. And then you have local Lorentz and local position invariance, which say that in any local freely falling frame, the frame's velocity or position do not matter, in the sense that the outcome of any non-gravitational experiment is the same in any of these frames. And again, I made this point earlier already. In higher dimensional theories, there's new physics, new interactions typically, which will violate the Einstein equivalence principle at some level. So you can have massless scalar fields in string theory. Sometimes you have vector fields, sometimes you break Lorentz invariance, and so on. Obviously, the crucial part here is at some level. So in some theories, these violations would be huge, so these theories are rolled out already. In other theories, you have violations of the Einstein equivalence principle, but they are small enough to still be compatible with current data. But this is one motivation for improving these tests, because even if you find no deviations from the standard model, we rule out alternative models, so we learn more and more about universe. So theories obeying the Einstein equivalence principle are generically called metric theories of gravity. In those theories, space-time has a symmetric metric. Freely falling bodies follow geodesics of that metric. And in any frame that is local freely falling, You don't feel gravity, and non-gravitational physics laws are those special relativity. So in a sense, you can, as a sort of mental image to have, if the Einstein equivalence principle holds, gravity is a sort of fictitious force because you can always switch it off, in inverted commas, in your neighborhood by putting yourself in one of these freely falling frames. Another way of saying it is so gravity is just an apparent manifestation of a local geometry, of local curvature of space-time. And sometimes people also talk about the strong equivalence principle. So this contains the Einstein equivalence principle as a particular case. So the case where gravitational interactions are ignored. And if strong equivalence principle holds, you can think of strong equivalence principle as a statement that there's only and only one field that gravitates in the universe, and that field is the matter. So general relativity and the simplest version of Brainswicki theory, that some of you may have studied, are metric theories of gravity, but string theory is not. And in string theory unavoidably violates the Einstein equivalence principle at some level. And indeed, so this is true for string theory, but it is true for any phenomenological theory where varying non-gravitational couplings are the result of dynamical scalar fields. Okay, and so just before we finish for today, let me start with the concept of varying fundamental coupling. So we'll discuss it in a lot more detail tomorrow, but I want to give you a couple of theoretical concepts which are perhaps connected to what we discussed already in the last few minutes. So you keep them in mind for the beginning of the class. And just as a small self-publicity, there's a review article that I wrote some years ago on the topic, which you can read later on if you want. So this covers both observational aspects and theoretical aspects. It was written already 6 years ago, so some bits of it are actually quite out of date. The field has evolved quite a lot, but nevertheless, it describes in more detail the things that I mentioned already and will mention. So from a more pragmatical point of view, what are these things? Well, the short answer is we don't actually know, and that's part of the mystery. What we do know is that nature seems to be characterized by some number of physical laws and dimensionless constants. And historically, we assumed that these are space-time invariant. They're the same at any time and everywhere in the universe. And for the former, for the laws themselves, this is pretty much a cornerstone of the scientific method, right? It's hard to imagine how one could do science if this was not the case. If the laws of physics were different today and tomorrow and so on. Or were different in the room where I am and in the room where you are. So you need to assume this for physics laws, at least to some level, just to be able to do science at all. So that these laws exist, that they're not a construct of our mind, that they're whatever they are, they're out there, and in principle we're clever enough to at least try to understand what they are. Okay, so this is true for the physical laws, but it doesn't have to be true for these dimensionless fundamental couplings. There's nothing in our theories that tells us that they should be really constant. So the fact that they are constant, or that we assume them to be constant, is a simplifying assumption only. We don't have any deeper justification than that one. And of course, if they are not really space-time invariant, so if these couplings do change, then all the physics we know so far is incomplete, because obviously we haven't taken this into account. Indeed, we don't have any theory of constants, to use the term a bit in the first way. So we don't really know what role these things play in our theories. We don't even really know what the fundamental constant of nature is. In fact, the only definition we currently have of a fundamental constant is any quantity in our theories that we cannot calculate from first principles, but need to measure experimentally. So think of the electron charge, for example. Quantum electrodynamics, which is a hugely successful theory, there's predictions of quantum electrodynamics that have been confirmed to 10 places of decimals. Quantum electrodynamics does not tell you the value of the electron charge. You have to go into the lab, measure the electron charge, you get a number, then you put that number in quantum electrodynamics, and you can get these hugely successful predictions that you confirm subsequently in the lab. But we have no way in our theories to calculate the value of the electric charge. So that's why we call it a fundamental constant, because we can't say anything more about it other than it's a number we measure in the lab. So this is what I mean, that we don't have a theory of constants. So we just don't know what roles they play in theories. So this is another reason for something I said already. Testing whether or not these things are really constant or whether they vary in space and time is a crucial test of our view of the universe. And improved null results are important. A detection would, of course, be revolutionary. And if someone proves that these things do vary in space-time, that is a guaranteed Nobel Prize, a little bit like the Higgs. So this is the reason why, or it's a motivation to test it. And just to finish, since we don't have a theory of constants, there are several different ways of classifying them. One way of classifying them, which I find useful, is the one I put on the slide. It's not very creative. You just call them type A, B, C, D, and E. But it's one way of organizing things. So in this classification, you call type A things that are properties of particular objects, like the mass of a particle. So the mass of the electron is just the mass of the electron. It's not the mass of anything else, as far as we know. Then type B would be properties or characteristics of classes of physical phenomena. Type C would be really universal constants, which are relevant for all of physics and not just for some sectors of physics. And then, if to be a bit more specific, you can classify as a different group. So type D, what we could call invisible constants, constants which at least in a given model are 1. So one example is the ratio of inertial and gravitational masses, which in Einstein's theory, general relativity, must be 1. So type D are just constants that you expect to be 1. And then type E would be constants that you expect to be 0, mass of the photon, for example. Okay, so this is a classification. It's a choice. You can think of other ways of classifying it. But I want to also to emphasize that this classification is not rigid. And in fact, the way you classify constants can change with time. And let's take an example, which is the speed of light. So at the epoch of Galileo, for example, you'd say that the speed of light is type A. It's just the speed of light. And in that epoch, there was no fundamental theory for what light was supposed to be and so on. So it was a property just of light. So we classify it as type A. After Maxwell, so in the late 19th century, you'd say that the speed of light is type B. It's a property of electromagnetism. It appears explicitly in Maxwell's equation, so it's clearly a property of electromagnetism. After Einstein, you would now say the speed of light is really type C. It's a universal constant. It plays a role not just in in electromagnetism, it does play a crucial role in the universe as a whole, so it's clearly type C. So the way you classify a particular constant might change with time and might be different in different theories. Some quantities that you think as fundamental constants in the context of one model or one theory might not really be fundamental in another theory. Um, and in fact, you could also classify theories in some sense a little bit that way. Okay, so I think this is a convenient place to stop for today. So we covered a lot of theoretical concepts. We haven't looked at any data yet, so we'll start doing that tomorrow. But I think it's important for you to have a mental image of why we want to study some of these things before we actually get a little bit into more data. Okay, so let me stop sharing my screen. And so for the rest of the time, I'm happy to take questions. So either verbally or on Discord. So
We have time for a few questions, one or two. Raise your hand. Oh.
I have to stand up. Hi, Professor. Thank you very much for your nice lecture. I am a little bit curious. You said something like the introduction of new scalar fields will irremediably change the fine structure constant. I was thinking, what changing are you talking about? You are talking about not changing the renormalization group way, that you must couple your scalar field to the light to change this constant, define structure constant, or you are thinking in same classical variation that this scalar field rolls a potential and change this constant by a direct coupling with light. When you talk about this variation, is it a renormalization group variation of the constant with the scale?
Right. No, it's a different effect. So in a particle physics context, we know that these couplings run with energy. So alpha. So if you measure alpha in accelerators, its value changes with energy. So that's what particle physicists call running. So here we're talking about a different effect, which is a low energy effect as compared to particle physics. So essentially, your scalar field couples to the electromagnetic sector. So you have a coupling that depends on the scalar field. So essentially your gauge kinetic function depends on the scalar field, and therefore, because the scalar field is changing as the universe expands, your value of fine structure constant will change accordingly.
So it has to be
Depending on the
charged.
model.
The scalar field has to be charged.
No,
Electrically
you
charged.
can. No, just a plain scalar field can do it.
Okay. Thank you.
So we'll see examples tomorrow. The simplest way is to get just a time dependence. So you have a alpha depending on redshift, but you could also have spatial dependency. So you could have a dependence on the local density. For example, the value of alpha on Earth, which is a high density environment, could be different from the value of alpha in the background in the universe. We'll see examples tomorrow.
Thank you, Professor. Any other question? Well, I have one. It's a general one, taking the advantage of this class. Based on your said in the beginning of the talk of dark universe, in your opinion, so it's a matter of opinion, in your opinion, is the dark universe the Neptune or a Spock's home Vulcano?
I don't really know. I think if I had to bet on whether dark energy is a cosmological constant or a scalar field. If I was forced to bet, I would say it's a scalar field. Just because the fine tuning that you need for the cosmological constant is huge, right? 120 orders of magnitude, or 30 if you want to be an optimist, is just a huge difference to explain. A scalar field, to that extent, is more. I'm not sure if I would use the word natural, but at least it's less. It sounds less strange to me. But it's purely a matter of taste or aesthetics or opinion, without any deeper knowledge behind it. For the dark matter, I think I would still say it's probably a particle, an elementary particle of some kind. Whether or not it's a WIMP, I'm not sure. I mean, WIMPs were very popular some years ago. They still are, to some extent. I think, well, it depends who we ask, but I think it's probably still fair to say that they are the preferred candidate. But the constraints that people are getting on them, and the fact that they're not detected in the large number of experimental searches for them, is pushing things to a very peculiar corner of parameter space, right? And to some extent, you also need some fine tuning to get a WIMP type model giving you dark matter. And again, at some point, you might ask yourself, if I have to fine tune this so much, is there an alternative that is better? Now, I don't really know, so I don't work directly on dark matter. So there, I think my opinion is even less valuable than my opinion on the dark energy issue.
Okay, thank you. So let's thank him again.
Thank you. And as I said, if you have any questions, feel free to post them on Discord. I'll have a look at it periodically and answer any questions there. And in any case, I will see you tomorrow.
Perfect. Thank you very much.